Today, we're going to practice constructing truth tables in a variety of forms. So we begin with this example. Construct the truth table for the compound statement Q or not R and P or R. The first thing in constructing a truth table is figuring out what are the variables in this compound statement. So what are the first three columns that I'm going to have to use? Well, I have a variable P, a variable Q, and a variable R. So that seems like those are going to be my main three variables that I'm working with. And then everything else in this compound statement is produced from P, Q, and R by a variety of operations. The next thing to determine is how many rows am I going to have? So notice that this is the first time we have three variables and not just two. So I'm really going to have to think about what are all the possible combinations of P, Q, and R true and false values. So we're going to go through a similar exercise as we did last time. If P is true, then Q can be true or false. But for each of those two cases, R can be true or false independently. So it seems that for one case of P being true, I have four possible options for R. So when P is false, I'm going to have the exact same options, but for the case of P being false. Altogether, that actually results in 8 different combinations. And this is something that we are going to be able to prove is exactly the right number later on in the counting section. For now, we simply have this very crude way of showing that 8 is exactly the right number. So what I'm going to do is construct myself a table and start filling out the true-false values for P and Q as discussed above. So P can be true, Q can be true, R is true or false. And then Q can be false, whereas R can still be true or false. Okay, and that seems to be all of the options for when P is true. What I'm going to do then is P is going to be false, and I'm going to have the exact same Q and R structure repeated for the case when P is false. So I'm going to have true, true, false, false, true, false, true, false, whereas P gets repeated. It's going to become somewhat important in these longer truth tables to make sure that you actually are careful about the rows themselves, okay? So if you have lined paper, I strongly recommend to use it. And if you don't, I strongly recommend actually lining your table, because otherwise, if you simply misplace a value, it's going to have great impact on your actual result. Before we do that and make the table look a little bit more full, let's take a look at what our columns will need to be. So remember from last time when we constructed a table with compound statements, we wanted all the helper columns to appear. So first of all, I see that I need a column for not R. So that's going to be, let's say, my first column here. Then I need a column for Q or not R. So this will go here. The next one I'm going to need is going to be P or R, because remember, everything in brackets gets done first before the operation outside of the brackets gets applied. So P or R. And then finally, once I have both of those, I can compose them together with the final operation that is an AND here. So I'm going to have this column and this column. So the final column should always be your full expression that is derived from the previous columns. Excellent. Okay, so as I mentioned though, it's very important to keep things straight. So I'm going to line my table so I don't accidentally lose my placement and therefore somehow work with the wrong values, because simply my handwriting is misaligned somehow. Okay, now let's go through. Again, it's better to go through column by column as opposed to row by row, because at least you're consistent throughout the operations. Not R is a column that involves only one variable, this R, and not R will be the negation of everything else in the R column. So true becomes false, false becomes true, and so on. So we simply follow the pattern of negating everything that is R, okay? So all of these values have to be exact opposites of each other. Excellent. Our next column is Q or not R. So we are going to have to look at the column Q, so this column right here, and the column not R, so this column right here, and connect them with the operation of OR. Okay, whichever way you choose to highlight that fact, let's say I'm going to point out to myself that these are the two columns that I'm now focusing on, Q or not R, and I'm going to go one value at a time in each one to fill in the corresponding spot in my new column. So Q or not R, true or false. I'm going to have a true. Remember that the operation OR is only false if both of the variables are false. So the next one is true or true, which gives me true, and so on. False or false, that's the only time my OR is going to be false. False or true is again true, because at least one of them is true. True or false is true. True or true is true. And you're beginning to see probably by now that these lines were very important, because just purely visual, it would be difficult to keep track, and maybe you will spot something in a different line. In order to be very organized and consistent, draw in the lines or take in the line paper so you avoid making silly mistakes. Okay, next one is false or false. That would be false. And finally, false or true, that would be true. Okay, this column is complete. The next column I'm going to take a look at is P or R. So I have to look at the column for P, look at the column for R, and I'm going to connect the two of them with an OR operation, just like in this previous case just now. So what do we have? True or true is true. True or false is true, and so on. So true or true is true. True or false is true. And in fact, notice that this half I could have filled in right away, because P is always true here, and OR is true if at least one of the variables is true. In this case, P was always true, so I knew that no matter what R was, all of these four values would have had to be true anyway. And then we have false or true, so still true. False or false is false. False or true is true. False or false is false. Excellent. Now we come to the last column that we have to put together, and that is our final expression. That is the previous two helper columns connected with an AND. So I'm going to have that I take this column and this column, and I'm going to connect them with a conjunction. Remember that AND is true only when both of your parts are true. So we have true and true is true. Next up is true and true, still true. False and true is false. True and true is true. True and true, still true. True and false is false. And the last two are going to be false, because at least one of the variables here is going to be false, which won't allow and to be true. Excellent. So this is it for this truth table. What are the lessons learned? Let's go through the process and see what were the important steps. The important first step was to determine what are the actual variables. So we decided they were P, Q, and R. The next step was to come up with all the possible combinations of those variables. So for 3 variables, we had 8 possible combinations of the true-false values. Then we needed to decide what are going to be all of the columns, and we went through sort of from the inside of the brackets out until we reached the final compound statement. Then we have lined up our entire table to make sure that all of our values don't get misaligned or lost, and then we filled out each column one at a time until we got to our final column. I know that so far it seems like we're constructing truth tables just for the sake of constructing truth tables, but this is a necessary practice before we're actually able to use them for some sort of higher purpose. Okay? Let's move a little bit away from directly constructing truth tables and think about how else can we use the logic truth values that we have just learned. In this example, we're going to practice working with a conditional a little bit more. Remember that the conditional is only false in the case of a broken promise. So if truth implies false, that is the only time that the overall truth value of the conditional is going to be false. Just to remind ourselves of what that looks like in terms of the truth table, let's quickly make one for P implies Q. Just a simple two-variable implication table. So what do we have? Our values for P and Q can be filled in. There's 4 possible choices. And for the conditional itself, the only time it's false is when truth implies false. So what I have here is true, false, true, true. Excellent. With that in mind, let's take a look at how we can apply this logic to these statements. If 3 is odd, then 3 squared is also odd. Now, we could be very formal and actually assign variable names. So we could call this P and we could call this Q. We could decide what truth value P is and what truth value Q is, and then look for that in the table. Now, because the statements here are fairly short, we can skip the maybe a little overcomplicating formality and analyze them directly. So what do we have here? If 3 is odd, so is this statement true or false? Is 3 odd? Yes, yes it is, which means that this is true. Then, what does it imply? It implies that 3 squared is odd. By itself, is this statement true or false? Well, 3 squared is 9. 9 is odd, which means that this is also true. Now, let's look in our table. What is the truth value of true implying true? Well, this corresponds to the first row here, and the corresponding truth value of the conditional is true. So overall, we have that this is true statement. Excellent. Next up, if banana is a vegetable, then an apple is an orange. Now, sometimes the statements make no sense, but we have to be objective and simply think about their separate truth values. So my first statement here is, banana is a vegetable. Is that true or false? Well, banana is a fruit, so this is certainly false. Then, an apple is an orange. Is that in itself, not in its entirety, but just this statement in itself, is that true or false? Is an apple an orange? Well, no. So this is false. So now I have to determine the truth value of the conditional where false implies false. And that corresponds to the last row in our table. False implies false actually corresponds to the conditional statement being true. This is what makes analyzing conditionals a little anti-intuitive, because things like this that are sort of meaningless in the first place might actually be true in the conditional. Again, remember, especially in the last 2 cases of the truth table here, we have what we call vacuously true. We start off with a false premise, and overall, it doesn't matter what the second half is, the overall conditional will still be true. So, if it's not the case of a broken promise, then it's going to be true. If banana is a vegetable, cannot possibly be true, which means that the entire thing is vacuously true. If Regina is the capital of Canada, then 2 plus 3 equals 5. Okay? Again, one piece at a time. Regina is the capital of Canada. Is this statement, the simple statement in itself, true or false? Well, Ottawa is the capital of Canada, so it's not Regina, which means that this is false. The second half, 2 plus 3 equals 5. Is that true? Well, 2 plus 3 is in fact equals to 5, so this is going to be true, which means that our overall conditional is false implies true, which in the truth table corresponds to this row here, and so the overall conditional value is going to be still true. Our last example, our exam is next week implies today is Friday. So remember, this is simply just another way of saying if then, so the implies can be replaced with an arrow. Our exam is next week. Is that true or false? Well, our exam is not for a while, so this is false. Implies today is Friday. When are you watching this video? Will that actually somehow affect the truthfulness of this statement? So today for me is Sunday, so for me, this will be false. If you're watching this on a Friday, for you, this will be true. But my question is, does it matter? No matter whether this is false or true, I'm starting with a false. So the row of the table I will be looking at starts with a false. So it's going to be one of these two. It doesn't matter what the continuation is. The conclusion is still going to be that the entire conditional is true. So independent of what goes in the second half, the conditional in this case is going to be true. Conditionals are tricky. We're going to need a lot of practice with them, so this is a good place to start. For the next example, let's go back to the truth table, but we're going to construct a truth table that involves quite a bit of variables, a few conditionals, and a biconditional. So we're going to have to, once again, be quite a little bit careful about how we're going to put this table together. Remember, the first step is to start with thinking about what are the variables. So here I have P, I have Q, and I have R. That seems to be both. So I'm in a similar situation as the truth table on top of this page. I'm going to have P, Q, and R as my variables, which also means that I'm going to have 8 rows for all of the possible combination of these guys. Now, I'm not going to fill in the rows yet. I'm more interested for now in what the columns that correspond to this complicated expressions are going to be. So what do I have? I have P, but I don't have not P yet. So this seems like the column that I'm going to need in order to work out the first bracket. Now in the first bracket, I have not P or Q, so I'm going to need a column for that entire thing. Not P or Q. Excellent. So far, I'm about halfway in because looking at the brackets here, the biconditional connects everything. So now I have to work out this bracket before I can actually deal with the biconditional. What do I have here? I have Q implies. Well, Q I have the column for. The implies, let's see, I'm going to have to work with this bracket first. Not R, I don't have yet. So I'm going to need a column for not R. Then I'm going to need the column for P and not R. Then I can finally have the column for my conditional here. So Q, because I have a column for Q, implies P and not R. So this guy right here, P and not R. Excellent. This is looking like I am almost done because the only thing that I'm missing, I have not P and Q right here. I have this big conditional over here, and the only thing I'm missing is the biconditional that connects the both of them. So my last column is going to be just that. Not P or Q, if and only if Q implies P and not R. Okay? I know it's tempting, especially when you've gone through a couple of these big truth table constructions, to start skipping columns. So I know it's tempting to say, oh, I can do not P in my head because it's literally just the opposite of P. And so I can do this at the same time as doing not P or Q, and therefore I can skip filling in this column. Inevitably, this leads to small mistakes being produced, and the problem, of course, is if you get this column wrong, then you're going to get the entire thing wrong because this column feeds into the last one. So I ask you to not, quote unquote, save time by skipping columns because it will result in mistakes, but rather be quite detailed in including every single column that you need to include before getting to the very last one. Again, I can fill out all of the values. There will be 8 of them. So in case of P, it's going to be 4 truths followed by 4 falses. And then the Q's will go 2 truths, 2 falses, 2 truths, 2 falses. And R's will alternate every single time. True, false, true, false, true, false, true, false. And again, let me warn you about another shortcut that inevitably somebody is going to take, is not lining up your rows. By the time you get to filling in this column, there will be already so many T's and F's in between that it's literally going to be impossible to keep track of that. So instead of making silly mistakes, I strongly encourage you to line up your truth table so you don't get truth values somehow simply misaligned and therefore incorrect because of that. Okay, I'm not going to go through filling in the rest of this table. I leave this as extra practice for you. One column at a time. This is nothing that we haven't done before already. So I have full faith in your ability to actually persevere through this exact truth table. As we continue to work with truth values and truth tables, we're going to introduce 2 specific types of statements. A tautology is a statement that is always true, regardless of the truth values of its variables. And the contradiction is exact opposite, is a statement form that is always false, regardless of the truth values of its variables. Let's try to think of some examples of tautologies and contradictions that we can construct from our already known values. So for example, if I start with some statement P and I put it together in disjunction with the truth, that will produce a tautology, right? Remember that or disjunction is true as long as one of the variables is true. So it doesn't matter what the value of P here is, this truth guarantees that the overall statement is going to be true, which makes it a tautology. Same, for example, if I have P or not P. No matter what value P takes, not P will be the opposite. So exactly one of them will be true, and therefore, connected with an or, it's going to produce a tautology. For contradictions, we can actually use very similar examples, but with an and. So for example, if I have P and false, no matter what P is, the and false guarantees that the overall truth value will be false. Remember that the and is true only if both of the parts are true, which is not the case immediately here. So the entire statement is guaranteed to be false because of this second half that is already false. Similarly, if I have P and not P, so instead of the or, as in the previous example, I'm going to have an and here, the exact same logic applies. P and not P will have opposite truth values, which means that at least one of them will be false, which means that the entire construct here will be false. Now, let's take a look at this example, which gets us working a little bit more with tautologies and arbitrary propositions. Notice that for extra practice, you can do the exact same example where you replace T for tautology by C for contradiction, and this will sort of produce more practice within the same types of example. So what I have is T is a tautology, which means it's always true, and P is some proposition whose truth value you don't know. So being the proposition, you know that its truth value is either true or false, but you don't know exactly which one. Whereas to find the truth value of each of the following 8 statements here. I'm not going to go through all of them, but I will do several that will be indicative of how you should proceed with the others. So let's start with the simplest one. Not tautology implies P. Well, actually, before we do this one, maybe let's take a look at the structure of all of them. They all have implication. As I said, implication, well, these ones have biconditionals. Implications are some of the trickiest ones to do, so we're going to do a little bit more practice with them than with the others. But before we do that, if it's going to show up in so many of these examples, it might be worth to just quickly go through and construct the truth table for it, so we remember how that works. Now, again, you're going to fill in all of the possible combinations of P and Q. And in case of the implication, remember that the only time it's false is in the case of a broken promise, true implying false. So it will only be false in this one spot here, and it's going to be true everywhere else. Now that we have this useful little cheat sheet on the side, we can proceed to take a look at these examples. So back to our first one. Not tautology implies P. Tautology is always true, which means that not tautology is always false. So in simplifying this statement, I have false implies P. Now again, P is some arbitrary proposition, so I don't know what the truth value of P is. And at this point, my goal is to find out whether or not it matters at all. So look, I have false implies something. So let's take this to our truth table for conditional and look for when false implies something. False implies something will correspond to these last two rows of the truth table because they start with false and then they will imply either true or false. But no matter what, my overall conditional will have the truth value. This is exactly the case for the vacuous truth statement, right? False implies anything will produce a true statement, which means that the answer in this case is true. And we can proceed in a similar manner through the rest of them. So let's take a look at this one. P implies tautology, which is always true. So again, I don't know what the value of P is. Maybe let me rewrite this as the actual true here that we know that tautology is equivalent to. I don't know what the value of P is, but I know that it implies true. So in my truth table here, I can look for rows where the second half of the conditional is true. So that would correspond to this row here and this row here. Notice that it doesn't matter what you start with. If, in this case, the second half is true, then the overall statement in both of those cases will produce the true as the overall truth value of the statement. All right, let's do one more in this row. Let's take a look at this guy right here. I have P or tautology, so I have P or true implies true. Remember, we're working from inside of the brackets out. So let's take a look at the truth value of this or in the first place. If I have P or true, remember how or works? It's true as long as one of the halves is true, which in this case is guaranteed to be true right here. So P or true is itself true. And now I have true implies tautology, which is also true. And this actually corresponds directly to just one row in my table, which results in the true as the overall statement of my conditional. Now, for the next one, let's take a look at the example here, which is kind of, feels like it has a very similar feeling to it, right? So let's take a look again, first of all, within the bracket here. We have P and true. So what does that actually result in? P and true. I don't know what the value of P is, once again. So I wonder, does it actually matter? Well, the and is only going to be true if both parts are true. And I don't know whether P is true or not. So I'm going to have to go through cases. I'm going to go through the two possibilities if P is true and if P is false. And I'm going to see what each of these possibilities actually entails. If P is true, then what do I have inside the bracket here? I'm going to have true and true, which is true, implies P, which I've set to be true. So implies true. Now, in this case, if I have true implies true, that corresponds to my first row in the truth table here. So the overall result will be true. What happens in this other case if I set P to be false? So I have false and true, which is false, implies P, which I've set to be false, so implies false. False implies false corresponds to this last row in the truth table here, so the overall conditional value is still true. So in this case, although we actually had to break it up into two pieces, both times we got true as the conditional statement, so this conditional statement is true independent of the value of P. If these two differed, then you would have to report both as the answer, but because in our case they both turned out to be true, then the overall statement is true independent of what value P actually is. Okay, this is the only other type of analysis that you can run into with only one variable and a tautology and a contradiction. One variable will only take on one of the two possible truth values, true or false. So worst case scenario, you will have to analyze both of the cases. I'm going to leave the other few examples for you to try out on your own, following the exact same pattern. Now, just coming back to our truth tables, let's do a little bit more practice with constructing the columns, just reminding ourselves what are the ways to do it, and also what are the possible questions that can arise in these types of constructions. We're asked to construct the truth table for not P implies R, implies Q, or not R. How many rows do we need is the question. What would be the columns? So, how many rows do we need depends on how many variables we have. And so what do we have here? We have P, we have Q, we have R. So that means that we will have a column for P, a column for Q, and a column for R. If we are to go through all the possible combinations of those columns, remember what we did a while back, then we will see that we actually have in here all the possible combinations will result in 8 rows, right? We will have 4 truths for P followed by 4 falses, and then for Q, we will alternate truths and falses half as often, whereas for R, we have to go through and alternate them every single time. Aren't you happy that there's no 4 variables where you will have to have 16 rows? Now that we've decided what the variables are and how many rows we need, we will have to move on to the next question. What would be the columns? And this always depends on the expression itself and how complicated it is, how many brackets there are, how many variables. Take a minute here and try to come up with the actual columns yourself before you go back to the video and see what I have. Remember, don't skip steps. Include every single column that is more complicated than the one before, so you don't make a mistake in your filling in of the table. So first, we will need a not P in order to deal with this first bracket. And then we are going to need the not P implies R that will form the first bracket that we have here in full. On the other hand, the second half has the column for Q, which we already have, and there's a column for not R, which isn't present yet. So I'm going to make a column for not R, after which I can include this entire expression, Q or not R. And once I've done that, I have formed the column for this bracket, I have formed the column for this bracket, so the only thing that remains is to connect them with a conditional. So not P implies R, all implies Q or not R. Be careful here, again, here and in every other example that looks like that you respect the brackets. Whatever goes in the brackets, just like in simple arithmetic, has to be done first. And only once you have the brackets composed are you able to connect them with yet another operation. So for this last column, when you're putting it together, you're going to look at the column for not P implies R and how that connects with the conditional with the second half of Q or not R. I'm going to leave the filling out of the table to you. Practice this. It's not very difficult. It's fairly straightforward. You just have to be really detail-oriented to get this correct, and that comes with practice. Let's take a look at these other two examples that work with truth tables, but not quite in the exact same way. So first one here, we are given that P is false and Q is true, and we're asked to construct the truth table for this expression here. Now, we could simply go through the exact same way we've done it before, ignore the additional information that's given to us, and construct the truth table for the entire thing. I'm going to have 4 variables here. So instead of 8 rows as above, I'm going to have 16. So it's going to be a gigantic truth table. So we probably don't want to do that. And this additional information is probably useful. So here I'm given that P is false. So I don't need to construct the truth table where P is potentially true because it won't be necessary at all. And I'm also told that Q is true, so I won't need to consider any of the cases when Q is false. So this will reduce my truth table quite significantly. Now, keeping that in mind, I realize that I know the value for P and I know the value of Q. I can replace them with their corresponding values right in the expression itself. So P is false and Q is true. Once I've done that, I see that I'm actually down to just the 2 variables, R and S. And that's all I really have to construct my truth table with, R and S. And once I have that, it actually becomes a fairly small truth table. Because for 2 variables, I only have 4 possibilities. True, true, false, false, true, false, true, false. And there we go. This looks much better than having a giant table with P, Q, R, and S. I'm down to only 4 combinations of the variables that I have to consider. Now, in constructing my columns, though, I still have to be true to the expression that I'm seeing. So this one, let's actually take it through the entire thing. So I have this first bracket, false if and only if R. So that is going to be my first column, false if and only if R. My next column is going to be not that. So not false if and only if R. And on the other half of my conditional here, I have true implies S as my next column. And then finally, I can connect everything with this conditional. So I have the entire expression now. Not false if and only if R implies true implies S. Again, brackets are important. And although there is like 2 of the same operation, you cannot just drop the brackets or do this one first. Follow the brackets. They tell you the order of operations. All right, let's fill this one out together. So, or actually better yet, pause the video, fill it out, and then come back to see how we can do it together. So the first column here, false if and only if R. Remember that the biconditional is like the logical equality. This will be true if the values are the same. So false equals to R, so true. No, that's not true. So this is going to be false. The next one is false. Is this equal to the R value? Nope, still not the case. False, is it equal to R? Yes. And then false, is it equal to false? Yes. So the last 2 cases here are going to be the truths. Then we have the negation of this expression. So we have the negation of this entire column, and we can go through one by one and simply flip the values. So here we're going to have true, true, false, false. Excellent. The next column is true implies S. Remember that the conditional is only false in the case of a fallen promise. So it's only going to be false if true implies false, right? Where's our cheat sheet table over here? Right here. The only time that the conditional is false is if we have true followed by false. So what do we have? We have true implies S. True implies true. That is true. The next one, true implies false. That's the one that's false. So this is going to be false. Next, true implies S. So true implies true again. This is going to be true. And then we have true implies S. So true implies false. Again, we have our case for when the conditional is false. Excellent. We're in good shape here because we're down to our last column where we have this not false if and only if are. So this column here implies T implies S. So it implies this column here. So we have to insert an implication between these two columns that are kind of very conveniently located next to each other. So what do we have? True implies true. That is true. True implies false. That is the false statement. False implies true. As long as we're starting with the false, it's actually going to be true. So this is true. And we have false implies false is also going to be true. And that is going to be the truth values for the expression that we were given. So again, remember that before you jump directly into constructing the truth table that you want to construct, if you are provided any additional information, take advantage of that because it can reduce the amount of work, the amount of rows in your truth table that you are constructing. Let's take a look at the next example. Again, we're told something about an expression. We know that this particular expression is false, and we're asked to determine all the possible truth values of this different expression over here. This doesn't seem like a truth table kind of ordeal, but it is using all of the rules that we've learned through the application of the truth tables. So let's start with the information that we actually have. We know that this expression is false. How can we decompose this expression? What is the main or like the last operation in this expression that you will be applying if you were to construct the truth table for it? The columns would be A, B, C, and then it would be not A, and then within the brackets, the column would be not C, B, if and only if not C, and then the last operation would be this conditional. So what we're actually told is that this last conditional is false. Now, this is really useful information because, again, remember, the conditional is only false if we have true implying false. So this expression being false actually tells us that that means that we start the conditional with the truth and we end it with a false. And now we can further decompose it into what it means for the values of A, B, and C. So now look, we know that not A is true. Let's write this down. Not A is true. Now, of course, that means that A is false. And that's great news because that actually gives us like the one very concrete value for A. A must be false no matter what. What do we have here, though? We know that B, if and only if not C, is false. Let's write it out separately. So we have that B, if and only if not C, is false. How can this expression be false? Think back on what does if and only if mean. If and only if means it's true only if the two values are actually the exact same. We're told that this is false, which means that B and not C have opposite values. So we have ourselves two possible cases. We have that either B is true and not C is false. So this is one possibility. Or the other case is the other way around. B is false and not C is true. Note here that I have to be careful to remember that it's B and not C that have opposite values. It's not the case that B and C have opposite values. I have to include this not in the if and only if equivalence. So I have these two cases. A is false no matter what, but then B can be true, not C can be false, or B can be false and not C can be true. Okay, so these are our cases. Now, I'm not asked for the values of A, B, and C. I'm asked for potential values of this expression here. So now I have to plug my two cases into this to see how they pan out. So let me maybe label them case 1 and case 2 so I have an easier way of tracking what is going on. So in my case 1, what do I have? The A value is false no matter what. So I have false or B. And in case 1, B is true. And then I have not B. Well, I'm still in case 1. So B is true, which means not B is false, or not C. And not C, notice how I didn't even have to actually solve for C. I'm given not C to begin with. So not C in this case is false. Okay, this is my case 1. And in case 2, what do I have for this expression? Following the same logic, A is false. Then I have or B, and in case 2, B is false. So or false. And not B, which in case 2 is going to be true. Or not C, which in case 2 is also true. Excellent. Now all I have to do is actually simplify these two expressions to figure out what their truth values are, because they correspond to the two truth values, or to the potential different two truth values of this. So I have false or true. Well, this is going to be, so maybe let me just write down a little equation or equality here. So I have false or true is true, and false or false is false. True and false is going to be false. And in this case, what do I have? False or false. So false and true or true is true. False and true is still false. So in both of my cases, I ended up with false for this complicated expression. So as long as I start with this as false, all the possible truth values of this expression are simply just false. Now note that if I did end up with two different values here, I would have had to report that. So I would have had to say that, for example, this is false if, in the case 1, A is false, B is true, and not C is false, or C is true. Okay, and in the second case, this is false if I have A is false, B is false, and C is false. Because they're the same, I can simply say that this expression is always false, but if they were different, I would have had to report the particulars of how they are different. Truth tables, again, it seems like they're a lot of work and these operations require a lot of practice, but as always, practice does make perfect. So do a few more of these examples, go through all of the examples in the lecture notes that I have not quite filled in, and we will see an application of truth tables and why they're important in the next lecture.